Hello, it's What the Doodle here, and in today's session I wanted to look at finite state machines, and these are things that sort of pop up now and then when you're building solutions in software. And most of the documentation I've seen, or most of the articles and tutorials, they seem to be really sometimes it can be a bit too much and too involved. But I just wanted to go over one, and I mean really they're not in abstract, or if in terms of very simplified form, they're not really that complicated. So here's this diagram here is very nice. It shows you essentially have something, you have a state, or you have a set of states that are known. So for example, this coin operated turnstile, you can imagine that there could be a locked position and an unlocked position. So essentially those would be the states, and obviously you have a starting point or initial state, which is sort of denoted by here, and then you have a set of inputs or actions that are performed that then causes certain things to happen to that state. And for example, when you insert a coin, it goes into the unlocked state, and this is called a state transition. And obviously if it's unlocked and you put another coin in, it's still going to be unlocked. And then obviously once you push the turnstile, that will then cause it to go into the lock state, and that's a closed, sort of a deterministic closed loop kind of thing. So yeah, they're very simplistic. So you can it's a way of modeling, if you like, a domain or a problem of space or something like that. So if, for example, in our example, what I'll obviously write it in Rust just to kind of show how it looks like in code and implement that. But an ATM, which is sort of where you draw cash out, essentially put your pin in. So you can imagine the states. Simplistically, we could say, for example, one of the states would be initially, or the initial state would be locked, and then we'd have a few more. So we'd have the lock states. When you enter a pin, it would be potentially unlocked. And obviously, if you enter your pin wrong too many times, it would essentially get blocked. So let's just put it on here, a block state. So we can imagine an ATM machine having these states essentially, and the actions between them. So for example, we would have an action that goes, sorry, let me just delete that one. So the action between for it to go from a lock state to an unlock state would essentially be when you if I get the text node here, when we enter a pin essentially. So enter pin. So if it's assuming that's a correct pin, obviously then it's unlocked. And then if you enter anything, I guess it can go back to locked. Or you could have some other things, like it could be time based. So after a certain threshold that it's left unlocked, it will automatically unlock. So again, that could be some internal logic there. So it could be also, it is obviously time related as well. Now we could have another node, for example. So that could be, let me connect that. So this could be, for example, when you've entered incorrect pin 3 times. So yeah, it's essentially, if it's from the locked position, if you enter the pin incorrectly 3 times, we can essentially suspend or lock that account or block that account, because we for safety reasons. And that would have to be then somehow, we could have other inputs where if it's a management or account or something, or management override or something like that, could then move back to unlocked. But I think just for this, because it's obviously a very simplistic example and I don't want to spend too long here, let's try and code this up in Rust. So okay, let's open up a new terminal, and what I'll do is I'll just make the screen a little bit bigger, so as usual you guys can follow along. And what we'll do is we will use cargo new, and create a new binary. Let's call it state machine, and then let's jump into that. Fire up our Visual Studio Code. We don't need the actual terminal anymore. So if we open up the main file. And let's see if I can make this a little bit bigger. Whoops, it's too big. Let's make it, maybe I think that's fine. And we'll toggle the terminal as well, which is good. We need that terminal. Let's make that a little bit smaller if possible. Nope, that's as small as it goes. Maybe if I make this, yeah, okay, that might be fine. So let's clear the mini terminal down here. Can I make that smaller? I'm not sure. Oh, I can. Yep, fantastic. Okay, so what we need is we need an enum, which is the traditional way that you would define those states. So let's call that state, which is not the most imaginative. But as we mentioned earlier, we have a locked state, we would have an unlocked state, and then potentially a blocked state. So that's those are three states of that of our finite state machine. And yeah, it seems to be able, which is fine. We haven't made any errors. That's good. So then we need a structure to define our ATM. So we could literally call this ATM as an example. And in the ATM, we would have that state, which is the actual state. That state enum of those three different states. We would potentially hold maybe the pin, which let's just model that as a string, and then the total number of incorrect pin guesses, or not guesses, but there you go. So that's our structure, if you like, the data structure. So we have internally a state. Internally we hold the pin, but obviously we wouldn't do it that way. Normally it'd be from some database or something, but this is just a contrived example. And then somehow in the actual internally we hold, we remember how many times a pin has been incorrectly entered. So we can now implement this ATM data structure, and we will have a new function which will just return a self. So this is the you initialize this new ATM data type or data structure. So the actual state initially, what we'll do is we'll set the state to locked initially. We'll set need to define the actual pin. I'm going to be lazy here. I'm just going to say 1, 2, 3. So that's our pin, and then the total incorrect. We're going to set that to 0 because it's a brand new instance, if you like, of that. So the only really functioning, obviously, this state or this application or this structure, sorry, could have state machine. Sorry, this state machine could have all sorts of kind of actions and inputs, which are the transaction. But in our transitions, but in our case, we only just have the one. So something like enter pin, and yeah, that's going to take a mutable. Oops, this is going to take a mutable self. And the actual pin itself, which is of type string, and then we return our self. So here what we can do is we can use the match, because oftentimes you'll see with enums they go very well with pattern matching, which is what we do here. And so these are like they go together very well. So because you have exhaustive matches on all of the branches, so therefore there's no way that you can actually make a mistake. Essentially, the compiler will force you to define each of the states, essentially each of the paths, if you like. So that's why they tend to go together very well. So we can say we're going to match on the actual state itself, and so now we have to go through each of them. So that forces us to think about what's going to happen. So when it's locked, we do a bunch of stuff. So we'll come back to that in a second. When it is unlocked, what should we do? And finally, when the state is blocked, what should we do? If I can type. Right, okay. Let's go back. Right, so of course, if it's in the lock state, what we want to do is we want to check the pin. So we will say, is the pin equal to the pin, basically? So have they essentially typed the correct pin in? If they have, we can then change this. We can then change the state transition to state unlocked, and then essentially return itself. If it's unlocked, sorry, actually, we need a bit more logic. If it's the wrong, if it is the wrong pin, so obviously this is the when the pin is correct, but we also need to handle when the pin is not correct. So what we'll do is actually we will increment the total number of times that's incorrect, because obviously yeah, so we need to handle that. And of course, if the total number of incorrect is, let's say, more than 3 incorrect, you've entered the pin incorrectly 3 times, then what we want to do, we want to set the state to essentially blocked if it's more than 3 times, or if it's been 3 times essentially. So state dots blocked, and then return the self, and essentially, yeah. No, we want to do that here. So yeah, so essentially what we're doing, if it's locked, if the state is locked, we check the pin. If it's the correct pin, we unlock it, so we do a state transition. Otherwise, if it's the incorrect pin, we bump up the number of total times that's incorrect. Then we check if it's greater than or equal. If it's essentially 3 incorrect tries, then we essentially do a state transition to blocked, and then return itself. If it's unlocked, what we'll do, it doesn't matter what you type in, we will just simply close it for now. So I mean, it doesn't have to be this logic, but we're just saying in that case. And I guess we don't even need these curly brackets. We can just return self on this one. So let's have a look. Let's have a look. Does that compile? Oh yes, ping. Yeah, I think I meant pin, not ping. So where have I done that? Line 25. Okay, let's have a look. Line 25. Line 25. Self.pin. You might have meant to use the available field. Okay, yes, sorry. Typed it wrong there. Okay, yes, so saying hello world, and that has compiled, which is brilliant. Okay, there's a few more things some nice things that we need, just so that we can print it out nicely. And what we'll do is these are the automatically derived, derive debug, and then we'll put that on we'll need it on the state itself as well. This is so we can actually print it. Okay, let's see if that compiles. Yes, it does. Okay, fine. So what we'll do, we'll say let's say ATM is equal to ATM new. So create a new ATM. Does it compile? I haven't saved it. Let's try again. Yes, it compiles. Fantastic. So what we'll do, we're going to print. We'll just say ATM state, and this is where that debug macro really helps. So we can just say ATM.state, and let's run that. So this our initial state of the new ATM state machine is locked. So then what we'll do is we will enter. Well, let's just enter a pin, and let's say it's the correct pin that we're entering. So entering pin 123. So then what we'll do is ATM dot enter pin 123, and then what we'll do is, so we've entered the pin, and now we're just going to print out the state again. So let's have a look at what happens now. Let's just do cargo format because I want the code to look a bit nice. Okay, and let's just run that. Cool. So now we can see that the initial state. Let me just make this a little bit. Okay, so you can see that the ATM state is initially locked. We enter a pin of 123, and now the state, as you can see, is moved to unlocked. So then what we'll do is we will just enter a random pin. So this time we'll just do like quit or something. Entering pin quit, and then let's grab the state and have a look. So yeah, we've got the initial state's locked, and we enter the pin, which unlocks it. We type in quit, and then that locks. Or we could have typed anything, to be honest, because our state, we've defined it here. We've defined that actually you'd have something like if pin equals to quit, then quit, or something like that. But or you could have all sorts of logic. But here I didn't bother doing that. And yeah, so then it gets locked, and then now what we'll do is we'll show that now that it's locked, we're gonna enter the wrong pin 3 times. So what we'll do, we're gonna 3 times. So what we'll do is we're going to enter the incorrect pin 3 times. And let's do this. So let's say, we've entered it incorrectly 3 times. Let's have a look at what our state's going to be. And hopefully, fingers crossed, when we run this, we should see that it gets blocked. There you go, that's it. So that is our state machine in essence. And so we start off with an initial state, and it's locked. We enter a pin, which is a sort of a state it causes a state transition, and it goes from locked to unlocked. And then we enter some garbage, some quit or whatever, and then we have another state transition from unlocked back to lock again. And then we enter the pin incorrect 3 times, and based on our sort of internal domain logic, if you like, we've defined it that if you enter the pin incorrectly 3 times, then the whole thing gets locked. And now here's the interesting thing: we can prove that. Let's say now we enter the correct pin after it's been locked. So we go, we're still in the locked, in the blocked state. And we now, as you can clearly see, this is the correct pin. But hopefully, let's just what we're going to do, we're going to put 1, 2, 3. So in theory, it should still be blocked, because it's not going to. It's not going to. It's not going to go from any other state. It's a terminal state essentially. So if you run that, and yep, that's exactly as predicted. So we let me just make this a little bit bigger. So we start off in the locked state. We enter the correct pin. It goes into an unlocked state, or transitions into an unlocked state. We then type in some commands, and the default action is to lock that account. Well, once it's from a unlocked position, it will always go to a locked position, whatever command you give it. And then once it's in a locked position, if you incorrectly enter it 3 times, we go immediately into a blocked and final terminal state. And then even afterwards, if you enter the correct pin, it doesn't matter, because it still remains on the blocked state. Now, of course, we haven't added any logic here that we could have perhaps a management pin that you enter, which then internally removes it back to the unlock state, so back to the lock state, that would be another state transition. And as I say, you can layer this in terms of complexity however you want, but it's sort of it isn't really all that complicated actually when you sort of boil it down. And as in Rust, essentially, it works so well by using these combinations of enums, and of course it can get even more sort of granular in terms of how you can model the actual problem domain, because each of these states, if you like, enum states, you can have data within them, and that will be specific to that state, and the actual logic around how you handle those state transitions. It just means, especially when you pair it up with the pattern matching of match, the actual compiler really forces you to define all these kind of different states, and you have to think about what happens in this state, and so it really is a nice clean way of modeling things, and it will be enforced by the compiler as well. So it all depends how you define your logic essentially. but it really helps to break down the problem and think about what are the universal set of states that your application could be in, and then you go from there, and it sort of all fits together like a nice sort of jigsaw puzzle, or not even a jigsaw puzzle. It's like a Lego block. You can only fit them in the way that they click together. So anyway, I hope hopefully that's shed some light on state machines and how they work. I mean, it's sort of a super crude example, but hopefully that was helpful. Right, until the next time, I'll see you on the next one.